Hello, everybody, and welcome to Physical Chemistry Lab. So today I'm going to be talking about computational chemistry. So specifically, I'm going to be talking about quantum mechanical calculations. Most of you have done some form of quantum mechanical computational calculations before. You are probably most familiar with this through the program WebMO. However, this semester, we're going to be using WebMO in much more of an open sandbox format, where I'm going to mostly be telling you guys what you need to accomplish, but not exactly telling you what tools you should employ at any given step. So the point of today is to give you a background into all the various tools and utilities you can use through WebMO. So we're going to be using WebMO this semester through the MU3C program. So this is the Midwest Undergraduate Computational Chemistry Consortium, which hosts a computational server at Hope College. And they graciously, through my research, let us make use of this in the classroom as well. So you should be able to log on to WebMO using the username and password that I've provided to you previously. If you still need a username and password, please go ahead and contact me. So one of the important things to know is there's many different computer programs that you can use even inside WebMO to model computational chemistry systems. So WebMO in this sense is pretty much the front end utility. It's what we're going to be interacting with and what's going to let us build our structures. But the actual calculations are run using a program called Gaussian. So when you're selecting what calculations to run, you're going to want to make sure to select the Gaussian engine. So I want to make note that a lot of what I'm talking about here today is going to be available in your in the physical chemistry lab notebook. And if you need a little bit more detail, feel free to read through that documentation as well as ask me any questions personally. So in terms of how computational chemistry works, essentially what we're going to be using is the Schrodinger equation. So the idea of the Schrodinger equation is I give my system a wave function, and then I can use the Schrodinger equation to figure out the energy of that specific arrangement of electrons. So this gives me the energy for a specific electron arrangement. However, this might not be the correct or optimum electron arrangement. So what the computer is going to then do is it's going to move these electrons just a little bit and see if it minimizes the energy. And it's going to essentially keep moving the electrons until I can't lower the energy anymore. And once it's done this, done several steps and the energy appears to be unchanging, this is what's going to be called the electronic energy of the system. So this is just the energy associated with moving the electrons. However, there's no guarantee that we started with our nuclei or our atoms in the right location. So typically the next thing that you'll do is you're going to allow the structures, the nuclei, to move around until their energy is moved. So essentially what ends up happening is I put in a guess structure, I optimize the electrons, and then the nuclei move a little bit. I optimize the electrons again. Then I move the nuclei some more, optimize the electrons yet again, and you keep doing this until essentially the electronic energy becomes minimized. So this first step of just running an electronic energy is often called a single point calculation. WebMO and Gaussian typically call this an electronic energy calculation. The second type of calculation is called an optimization. However, there is no guarantee that our minima structure is actually a correct minima. It could just be the case that I'm a minima in most directions, but I'm actually a maximum in a different direction, but the energy isn't moving that much because I'm a maximum. I have a first derivative of 0. So what we can then do is calculate the second derivatives on this structure. And this will help verify that we're a minimum. because if all of my second derivatives are positive, it means I'm at the bottom of an energetic basin. Now, one of the important things is this does not mean I am a global energy minima. I could just be a local minima somewhere on my potential energy surface. And this is actually a good thing because most structures we care about are local minima. Because if I was looking at global minima, well, it turns out that most complex molecules involving carbon and oxygen would eventually optimize to form CO2 because it turns out that's hecka thermodynamically stable. So this is something to keep in mind, is that we're essentially going to be comparing the energies of various local minima to figure out energies of reactions. Now, the second derivative also has another cool benefit. It turns out that these second derivatives also correspond to vibrational frequencies. So these are the same vibrational frequencies that we get from, say, infrared spectroscopy. Now, it's possible to then take these vibrational frequencies along with our electronic energies and use these to determine the enthalpies and Gibbs free energies for a molecule. So if I know my electronic energy, I use some statistical mechanics along with my vibrational frequencies, I can get my enthalpy, Gibbs free energy, and consequently entropy, as that will be related to the difference in between these two. So this is actually a really powerful way to make use of computational chemistry. However, we kind of also need to look at these individual components to really see what's happening and how we can try and optimize our the best way to approach these overall goals of generating thermodynamic values. So again, what the computer program is really going to be doing is trying to solve the Schrodinger equation, where here H is going to be our Hamiltonian, psi is our wave function, which essentially is what as a way of describing the arrangement of the electrons, and E is really what we're after. It's the electronic energy. Now, one of the biggest problems is that we don't actually know what the true Hamiltonian is for a system that has multiple electrons, even with a single atom. We essentially have to use approximate Hamiltonians. And this is the real art of physical chemistry and quantum mechanics in general, is trying to essentially figure out what's going to be the best Hamiltonian. And each of the computational methods I'm going to talk about today has a different approach to trying to solve this equation. Most of them focus on using separate Hamiltonians. Some play around with trying to use different wave functions to make solving the Hamiltonian easier. And one of the things that we're going to try and focus in on is this kind of classic trade-off in between computational accuracy, so a method that gives you good results, good energies, and methods that are fast. As a general rule, faster methods are very inaccurate. Accurate methods are very slow. So we're going to essentially try and walk our way up the description of accuracy. So one of the least accurate methods is called the semi-empirical method. So the general approach of a semi-empirical method is saying, well, I know one electron Hamiltonian pretty well, and for all of the electron-electron interactions, well, I've got a lot of experimental data I can use to kind of parameterize these interactions. So I'm going to pre-solve most of those integrals for electron-electron interaction, and it should work pretty well. Now, as a result, because most of the integrals are already pre-solved, these methods run very, very quick. But they tend to suffer a couple major problems. First, they're only going to be somewhat accurate for systems that they've been well parameterized on. So essentially, systems where a lot of experimental data came from. And that tends to mean mostly optimizations of organic molecules. So if all you're trying to do is optimize an organic molecule, no conjugation, pretty simple, they're not bad. And as a result, they're actually used to model a lot of biological systems up to the size of proteins. Because they run fast enough, you can actually model fairly large systems, and that's mostly just organic, so it works okay. Another major problem is they tend to do what we call localized electrons. So most of the time, electrons are hanging out fairly far away from atoms. There's a lot of combination between electrons on different atoms. Electrons hate staying on a single atom. Well, as part of this parameterization, semi-empirical method overly localizes these wave functions. So as a consequence, these methods are also very poor for methods with a lot of electron delocalization. So think about conjugated pi systems, think about metals, and even think about atoms that have a little bit more delocalized electron content, like oxygen and nitrogen, with those lone pairs giving a little bit more flexibility. So in that sense, semi-empirical isn't that good. However, if you ever want to generate a really pretty molecular orbital diagram, do it with semi-empirical methods. They're utterly beautiful pictures. The energies are inaccurate, but they're beautiful pictures. So consequently, most of the time, if you're going to use a semi-empirical method, it's going to be mostly used for very large systems, or if you have or if you need to quickly generate a rough structure. Because it turns out that iterative process of structure optimization is very bad if you start fairly far away. And because semi-empirical method is fairly cheap, it can get you to an approximately right structure pretty quickly. However, for most of what we're doing, while you can try and pre-optimize your structure with semi-empirical, you're almost always going to want to follow up with a better method. So one of the first of those better methods is called the HartreeFock method. So the idea of HartreeFock is it kind of does what semi-empirical starts to do, but it does it right. So it starts by essentially calculating the energy of every individual electron orbital or pair, while treating all of the other electrons as static. And then once you've optimized that electron, you then optimize the next and the next and the next. So it does it through this kind of iterative process till the system stops changing. So it actually does pretty good for kind of a static electron structure, but it misses an entire host of properties called electron correlation. So electron correlation can be split into two major categories. The first of which is called dynamic correlation. So this is essentially the idea that if electrons are not stationary objects, and if one electron moves, we're going to find other electrons moving in response. So the classic example of this is London dispersion, where you have two big, long, greasy chains of molecules. One electron moves, an inducing dipole in the other molecule. And in truth, when you average out this movement, you actually get something that looks dynamic, but it's all based on essentially an average set of correlated electron movement, thus dynamic correlation. And HartreeFock misses that entirely. So as a consequence, if you have a system with a lot of non-bonding energies, especially a lot of induced dipole, HartreeFock is going to let you down. And this is something to be very aware of. Furthermore, it also misses an entire set of properties called non-dynamic correlation. So this is essentially the idea that if I have multiple molecular orbitals that are degenerate, so they share the same energy or they share very similar energies, what will actually happen is you'll have a single electron occupying multiple of these different orbitals. So one of the cases that this is very common is in metals, who tend to have a lot of degenerate orbitals, but you'll often see this in long conjugated organic chains. So think about pi networks. As a result of those pi networks, you often get these degenerate orbitals. And again, HartreeFock absolutely fails at these. And due to these kind of paired effects, essentially HartreeFock will only be good for a very small organic molecule. So if you're studying methane or ethane, it's not bad. If you're studying anything else, we kind of need something a little bit better. One of the other things to make note of is that calculation time for HartreeFock scales is n to the 4, where n is essentially related to the number of electrons. However, this does mean kind of something interesting, because we think that we tend to want to think that if I double the size of a molecule, I should double the amount of time it takes. Turns out what happens is it's going to take 16 times as long if you double the size of a molecule. So it means that computational methods tend to be very sensitive to the size of the system. So even if you're truncating out small groups on the end, it might not seem like things are changing that much, but because of this exponential relationship, it can actually significantly shorten the time of calculations. So there's several ways you can try and improve on HartreeFock by essentially adding in dynamic or non-dynamic correlation. These essentially can be done using a classic physics approach of adding in perturbations, where you essentially allow in a little bit of electron movement. But it's worth noting that when you do that, you take the, first of all, each individual step takes a lot longer. And second of all, that time scaling goes from, say, n to the 4th to, say, n to the 6th if you're dealing with MP2, to if you're using couple cluster, which we're going to use at certain points this semester, you're talking n to the 8th to n to the 12th, depending on exactly which method. So those methods are going to be very slow. So HartreeFock, not too slow, but fairly inaccurate. Those post-HartreeFock methods like MP2 or couple cluster, fairly accurate for MP2, very accurate for couple cluster, but very slow. So we need is something in the middle. So our big workhorse computational method is called DFT, or density functional theory. So density functional theory takes solving the Schrodinger equation and turns it on its head. So instead of trying to solve our electron energies in terms of molecular orbitals or wave functions, like HartreeFock, instead what we're trying to do is optimize the electron density. So this is going to be the same as the square of the wave function. One of the benefits of the electron density is that this is an actual measurable property. So we can actually measure the likelihood of finding an electron in a given location. That's the electron density. And it turns out that we can actually generate exact equations for most of the features of that contribute to the energy, specifically the kinetic energy of the electrons, the interactions of the electrons with the nuclei, the interactions of the nuclei with each other. However, it turns out there is actually no exact form of equations to try and describe the interactions of the electrons with each other. In this case, we end up with the same problem we did with HartreeFock. So there's essentially a series of approximations we can use. The first of which is called local density approximation. So what this does is it uses a pre-solved physics approach where they're able to determine the exact electron-electron interaction energy for a system that has the same density at every given location. So if I say optimize my system, I know what the electron density is in one given location. I can then just use that as the interaction energy for the electrons. That should give me my exchange and correlation. Generalized gradient approximation, often called GGA. So what this does is it uses that local density from LDA, and then it essentially also adds in a dependence on the first derivative of that density. So when I'm calculating my electron interactions, I need to not only know the density of electrons at every given point, I need to know the change of that density. And using that, I should be able to find out electron-electron interaction energies using GGA methods. Unfortunately, there is no fully analytical method for GGA. So you often need to have some form of parameterizing your equation for a GGA method. So where there is only a single LDA method, there's actually many different GGA methods. The most popular of which that you'll have access to is called PBE. And this is actually a fairly good method. It does a very good job for a lot of metal containing systems. However, if the first derivative is good, the second derivative might be better. So there's something called meta GGA. And so this uses the local density and both the first and second derivatives of the density. I tend to be a very big fan of using this system, especially when dealing with metals. And the two of the more commonly used meta GGA methods are called TIPS and MO6L. And both of these are very good for metal systems. And they also tend to both be very good when dealing with non-bonding interactions because they model that dynamic correlation from things like London dispersion very well. However, it turns out that DFT is not perfect. It tends to have a couple systematic failures. So one of the biggest ones is that you can't really use DFT to describe any variable that includes molecular orbitals. So it's going to do a very poor job of describing any MO-dependent property, such as HOMO-LUMO gap, UV-vis spectra, ionization energies, because all of these are dependent on the energy of the molecular orbitals. And because DFT is optimizing the density, it kind of generates an ad hoc set of molecular orbitals, but they're not very good. Consequently, if you're trying to take pictures of your molecular orbitals, don't use DFT. Try and use something like HartreeFock, or honestly, even a semi-empirical method can be better at molecular orbitals than DFT can. And this is an unfortunate reality. One of the other things is that it does not include some quantum mechanical properties. So the biggest one is called electron exchange. So electron exchange is essentially the idea that electrons are indistinguishable. And this means that there is a tendency towards a certain degree of overcounting when describing electron-electron interactions. It also tends to avoid a lot of properties, such as the fact that electrons of different spins will actually interact with each other differently than electrons with the same spin. And this is, again, an unfortunate factor that DFT never quite is able to nail. But practically, one of the biggest things is that DFT tends to overly delocalize electrons. So because it's optimizing this density, it tends to spread out molecular orbitals a little too much. They get a little too thin. However, it turns out that that actually can be to your benefit sometimes. So if you have a system with a lot of non-dynamic correlation, where your electrons are spread over multiple molecular orbitals, well, it turns out that DFT can actually describe those pretty well, almost by accident. So this is one of the reasons why DFT methods like PBE and MO6L tend to actually be pretty good at metals, because they get this over-delocalization of, they over-delocalize the electrons to a certain extent that you are going to see in metals. However, if I'm dealing with a lot of organic molecules, like we are going to in this class, well, I probably should try and stay away from a pure DFT method. But what I can do to help correct for some of this is that it turns out that there's a method that perfectly solves electron exchange. It's called HartreeFock. So what we do is we blend in a little bit of HartreeFock with our DFT method. So typically what you'll do is you'll account for about 25% of the electron exchange from HartreeFock, mix it in with your, replace 25% of your electron exchange as described by DFT, mix them together, and this generates what's called a hybrid method. So these hybrid methods tend to have about an appropriately localized set of electrons. They're still a little bit more overly localized in reality, but not nearly as bad as a pure DFT method. However, these hybrid methods also tend to be very good at describing organic systems. They tend to get a lot of things like equilibrium constants and rate constants pretty spot on. So the major hybrid methods that tend to be used in reality are B3-lip, PBEO, also known as PBE1. The idea here is there's one parameter, and that's the extent of HartreeFock exchange. Everything else is derived as much as possible from physical principles. And MO6, which tends to be based on comparison with experimental data. So PBE, the idea here is that they try to model the system as much as possible on pure physics. It tends to be very good for metal systems, especially condensed phases. MO6 tends to be very good for organic systems and organometallics, which it's been very well parameterized on. B3-lip was essentially the first major hybrid method, and it tended to work kind of by an accident, a lot of cancellation of error. So I will say that B3-lip tends to do a surprisingly good job at describing systems, but it is very vulnerable to idiopathic error because you never know when those cancellation of errors are going to kick in. But these tend to be the three biggest methods in use. And if you talk to a computational chemist, they're going to tend to support one of these three functionals very, very heavily and have cruel things to say about the other two. Guess which camp I'm in. However, one of the things I do want to try and emphasize is that these hybrid methods, they are a little bit more expensive than a pure method because I'm essentially doing a HartreeFock calculation and a DFT calculation. But it is worth noting that it's usually a cost that's worthwhile if you're trying to describe an organic system, which is going to tend to be what we'll do in this class. Now, one of the other important things to acknowledge is that when we're dealing with HartreeFock and DFT, our molecular orbitals and our electron densities have to be constructed from some set of mathematical functions. I need some set of mathematical functions to model my electrons that I can then optimize using my Hamiltonian. So the classic simplest choice we can try and make is using the hydrogenic atomic orbitals. So these are the atomic orbitals you learned in Gen Chem that were built up for a hydrogen atom. And they tend to follow an equational form with regard to radii that's called a Slater type orbital. So it's a function, it's a negative exponential function with a with an exponent of negative alpha r, where alpha is just a constant. But here's one of the problems, is that it turns out when you're trying to integrate these Slater type orbitals, they're terrible to integrate. They take a long time to integrate. It isn't actually that easy. So one of the approaches that it's most typically used is you try and take multiple Gaussian type orbitals. So these have a form of negative alpha times r squared. And it turns out that this r squared actually makes these integrals much easier because most of them tend to have analytical forms that you can literally just look up in a table. They are pre-solved. They're very nice and easy. And because of that, it actually takes less time to try and integrate three of these Gaussian type integrals that have essentially been added together to form an orbital that looks like a Slater type orbital. And this is called STO3G, Slater type orbital made of three Gaussians. So this was one of the first big basis sets. However, it turns out that this basis set isn't exactly the most flexible. So one of the things we can do is, so you can imagine that the core electrons are made of three Gaussians. Well, the core electrons aren't really going to be moving. So I can treat all my core electrons with three Gaussian orbitals combined in a fixed format. However, those those valence electrons, I need a little bit more flexibility. So I'm still going to make my valence electrons as an additive by adding together 3 Gaussian orbitals, but I'm going to fix 2 of them in a set ratio, and I'm going to allow the ratio of that third orbital to change. So I could have more of that third Gaussian or less. And this gives us essentially a lot more flexibility in how far out the Gaussian can be. It can go out, it can come in, it can move around. And by getting that little bit of extra flexibility, it allows the system to combine with other molecules in a lot easier fashion. So this essential idea is I'm using the same functions in both cases, except for in this case, I use 3 Gaussians that are essentially combined in a set fashion. Here I'm pairing them together into 2 sets of Gaussians where the ratios can change. Now you can expand this idea so that I'm going to include more Gaussian orbitals to describe my valence electrons. So anything before the dash is going to be the core electrons. So I'm going to describe all my core electrons with 6 Gaussians, which means I get a very good description of core electron behavior. They don't need much flexibility because core electrons tend to stay static. And then I can add in an extra Gaussian into my valence electrons. So now I've got a set of 3 Gaussians with an extra Gaussian of varying ratios to give more flexibility. And I can add even more flexibility by adding in an additional Gaussian. So again, here I'd have 6 Gaussians describing my core electrons, 5 Gaussians describing my valence, in essentially 3 sets. So the ratio of these 3 sets of Gaussians can essentially vary. And you can kind of see how this works. So if I have a Slater type orbital, it has essentially a certain sort of behavior, a nice little peak, and a set curve. Now, if I use a single Gaussian, I model essentially most of the orbital pretty well, but I do a very poor job of modeling the electron distribution near the atom. I can improve that by adding in more of these primitives. So these are those extra Gaussians. So by adding together 3 Gaussian orbitals, I get an equation, I get an STO3G orbital, which does a very good job of mimicking the original hydrogenic orbitals, except for it gets the electron density a little bit wrong, very near the nuclei. However, since this isn't widely interacting, it's not too bad. However, again, one of the problems is that by keeping these primitives in set ratios, I have no flexibility. My orbital will always look the same. And this is okay if I'm just modeling a single atom, but if I'm trying to model chemistry, I need this orbital to be able to move in response to the presence of other atoms. And so you can do this by, say, allowing one of these orbitals to have more say. So that would essentially mean that, say, if I have more of this center group, I localize more of the electron density on the atom. And if I decrease the amount, well, it's going to, by necessity, spread out more. And by allowing the ratios to change, I get a lot more flexibility. However, one of the things that is worth noting is that every time we add an additional primitive, it is going to drastically increase our computational time because that n to the 4th time dependency actually doesn't apply to the number of electrons. It really applies to the number of primitives that you're using to analyze your system. So that is an unfortunate factor. However, adding in additional primitives isn't going to be the only way to model the system. One of the other things you can try and do is add in what's called a polarizing function. So let's say I'm trying to model something like a hydrogen bond in between 2 amines. Now, it turns out that if I try and do this just with the hydrogenic orbitals, this bond angle will be exactly straight because the only function on that hydrogen atom is going to be s orbitals, which means that if which means they can only really interact in a straight line. Now, in order to get real kind of bond angles down, I need to give a little bit more flexibility. So one of the ways we could do this is, say, adding a primitive to that hydrogen orbital that gives a little bit of p character. So it's able to get a little bit more angle character. Similarly, you could allow nitrogen to deviate from a typical tetrahedral structure if you added in an extra couple of primitives representing your d orbitals. And this is really the idea behind a polarizable basis set. So if I was going to polarize my system, I'll add a p orbital for hydrogen and helium and a set of d orbitals for all of my second row elements. So this is boron through fluorine. And this can be, and you'll often see this represented as you'll take your original basis function and you'll add in a d to representing adding in those d orbitals for second row elements and a p to add in p orbitals for hydrogen. Now, it is worth noting that these won't drastically affect energies, but it is entirely possible, especially if you are expecting deviations from ideal geometries, that you're going to need to include a polarizable basis set in order to get a correct geometry. We also tend to see similar problems if I'm dealing with a negatively charged atom, because if I negatively charge a molecule or an atom, I would expect my orbitals to essentially grow, because the electrons are going to want to stay farther away from the nuclei because they're all jostling each other out of the way. Now, unfortunately, the orbitals as written don't tend to have enough room for all of these electrons. They don't allow that growth, even with the addition of primitives. So one of the easiest ways you can try and do this is add what's called a diffuse function. So this is the idea of this diffuse function is you're going to place a single set of, again, Gaussian functions or primitives that are at longer distances from the nuclei. So the classic approach is you'll just add in a single primitive for a set of orbitals of a higher principal quantum number. So if I'm having, say, a 2s orbital, I'll add in a primitive for a 3s orbital, which allows that little bit of extra growth, especially as you're adding in only a small percentage of that 3s character. And again, just the addition of that extra primitive usually gives enough flexibility for a good optimization. These diffuse functions are often represented by adding in a plus. So a single plus essentially is going to represent adding in an extra set of 3s or 3p orbitals if I'm dealing with carbon, oxygen, nitrogen. If you add in an additional plus, that would represent adding in an extra 2s function for hydrogen. However, typically we do not need to add in a diffuse function for hydrogen. However, hydrogen does often need that polarizable function. So hopefully with this information, you know how to correctly choose a functional and a basis set to model the systems that you're going to be talking about all semester. However, one of the things to acknowledge is some of these projects involve trying to include solvation effects. So one of the cheapest ways to essentially describe the interaction of a molecule with the solvent is to use what's called a polarizable solvent model. There is one available in Gaussian. And what this essentially does is it embeds your molecule in a field of charges. And it allows these charges to essentially adopt positive or negative character depending on how close they are to certain units on an atom or on a molecule. So if I have a negative charge here, I should expect to induce a slight positive charge in my surrounding solvent. However, sometimes we're going to be in water, sometimes we're going to be in ethanol. How would I represent the differences of those solvents? And the idea is to use what's called a dielectric constant. And the dielectric constant pretty much describes the extent to which that solvent is polarizable. So not too surprisingly, water has the highest dielectric constant. Something like cyclohexane is going to have a very low dielectric constant because it's going to be very bad at generating charges. So hopefully I've given you a brief overview of some of the important factors that go into choosing a computational method. I have provided a lot more detail in your in your lab manual. However, if you ever need to ask, need any additional help, feel free to ask me or the TAs any additional questions. See you in class. Take care.